In this video, we're going to continue our look at some t-tests. In this one, we're going to be looking at example where we have a paired data set. So just as we did with a paired data on a t interval, when we have paired differences such as before and after measurements, this is one of the most common and useful situations. But remember, it's not really two samples, but rather one sample of ordered pairs. So what we do is we compute the differences within each pair after minus before, and so that a positive value on the difference gives us an increase and a negative represents a decrease. And then treat it as one sample of differences. So now it's just like before. And of course, you can use a one sample z-test if the population standard deviation is known. But much more often, like what we're going to do in this video, we'll use a one sample t-test when the population standard deviation is unknown. So let's look at an example here. In USA Today, September 17, 2009, a Bloomberg News poll was quoted to find that Americans were planning on keeping spending down. Suppose a group of 15 households noted their household spending in March and then noted their household spending 6 months later in September. The mean of the paired differences in spending was calculated to be negative 75.50 with the standard deviation of 66.20. And those are, of course, in dollars. Does this sample give sufficient evidence of decreased spending at the alpha equals 0.05 level? And then what is the 95% confidence interval for the change in monthly spending? So we'll do both the hypothesis test and a confidence interval here. Well, notice that we're testing means with the population standard deviation unknown, and now we do have a sample of only 15, so we would hope that these differences are somewhat close to normal, or at least not highly non-normal for this to work. But let's assume that that's the case. Then we can use a t-test here, a one sample t-test. The null hypothesis is that the change in mean is 0, that basically it didn't really change any. And the alternative hypothesis is that the change is negative. The change is less than 0, the mean change. So in other words, the mean of the differences, mu of the differences is 0 is the null hypothesis. That mu of the differences is less than 0 is the alternative hypothesis. So it's a left-tailed t-test, one sample. And we can go ahead and work this out with our calculators. Okay, so we can use a t-test. So on a TI-84, for example, you could do stat, go to test. We have summary statistics. The mu naught is 0. The x bar is negative 75.5. The s of x is 66.2. N is 15. And we're doing a left-tailed test, so we're testing that mu is less than mu naught being 0. And then we calculate that. So I clicked on calculate. You could also draw, which will draw the t-distribution PDF. But here we're going to calculate. There's the alternative hypothesis again. There's the t-test statistic. And more importantly, here's the p-value, which is the main thing we need. Remember, this e-4 means times 10 to the negative 4. So that's 0.3 zeros, then the 29. So the p-value is 0.00029, which is a very small p-value. So it's highly unlikely that you would see this big of a drop in average if this was just a random variation within the sample there. So we knew it was going down some because of the differences here, but was it enough to be reasonably sure beyond a reasonable doubt that the change was due to a difference in actual behavior and not just a kind of a fluke of a random sampling? And in fact, with this low of a p-value, we're very sure. We have very strong evidence to conclude that Americans average less in household spending in September than in March. How much less? Well, our best guess is about $75 less, but we can get a 95% confidence interval for the mean change in spending by doing a t-interval on our calculator. So now go back to stat and test, but this time go over find t-interval in the list. And again, it's from statistics. Make sure this is the same data in x bar, s, and n. Confidence level is 0.95. this says calculate where this black thing is here, so click on that, and out pops this confidence interval, which is about $112.20 less to $38.84 less. So we're 95% confident that they spent at least $38.84 less than what they did 6 months earlier on average, and that that could go up to as much as $112.20 for that month. Okay, so there's an example of this. Here's a similar one that I'd like you to do for an exercise. So after you read through this page, then you're going to pause this, work it yourself, and then come back and check your answers. So here we have 10 subjects with borderline high cholesterol levels. They were randomly recruited for a study that involved taking a nutrition education class. Cholesterol readings were taken before and 3 months after the class, and the following table gives the results. Is there sufficient evidence to support the conclusion that the class helped lower cholesterol levels? Use alpha is 0.05. What's a 95% confidence interval for the mean change in cholesterol? So do both a hypothesis test and a confidence interval. Press pause now. Okay, so let's take a look at the answer here. So notice that we're doing before and after data. So this is one sample of ordered pairs, so we find their differences, post-test minus pre-test, and we see that a lot of them are negative, meaning they went down. There's one that went up there, but we have some data that's paired like that. Is there sufficient evidence to support the conclusion that they lowered the cholesterol levels? Okay, so what we do is we need that difference data in our calculators. So one way we could do it is actually type in the pre-test data in L1, the post-test data in L2. So go to Stat Edit, go put your cursor on L1, clear, enter to L2, clear, enter, put it on L3, clear, enter. So you start with 3 blank lists, type your data in L1 for the pretest, type the data in post-test in L2. Be sure that you're typing it in the same order so that the first row is the same subject, the second row is the same subject, and so forth. Then put your cursor on L3 and type in L2 minus L1 and enter. Okay, and then it will compute the differences. Remember, our data that we want to work with now is the differences, which is in L3. So now go back to home by doing quit, then do a t-test, and this one is done from data. Mu naught is that there was no change. It was completely ineffective. There would basically be no change, so that's 0. Our data of differences is L3. And we want to do a left-tailed test because we want to see if this number is below 0. So we do mu less than mu naught and press calculate. Notice it gives us our alternative hypothesis, mu less than 0, gives us our t-statistic, our p-value of 0.0039, an x-bar value, an s-value, and an n-value for that sample of differences. Since the p-value 0.004 is less than 0.05, considerably less, then we know that we do have enough evidence to support the conclusion that this group was having a lower cholesterol levels, and so there's some reason to believe it may have been from this class. How much are they going down on average? Well, we see that X bar is about 26.3 in the whatever scale the cholesterol is using there. And we could give a confidence interval for the mean, which of course have that X bar right in the middle of it, by doing a t-interval on our calculators. So now go back to stat, test, but this time choose t-interval. Choose it from data, that should say there, L3, frequency 1, confidence level 0.95, I think is what they asked for, yep. And then calculate there, and here's our confidence interval. So the conclusion is there is sufficient evidence to suggest that the cholesterol went down, and so therefore it might be from this, good chance it was from this class, and the amount that it went down on average we're 95% sure is somewhere between about negative 44 points and negative 8 points. So we see that this has our conclusion here.